and welcome to Module 16. In this module, we'll explore cosmology, theology, and the quest for the unknowable. Cosmologists study the origin, structure, and creation of the universe. Einstein's general relativity, as originally structured, predicted an expanding universe. He was so uncomfortable with the idea of an expanding universe that he rearranged his equations to eliminate this expansion. Our current understanding of the expansion of the universe is that space-time is something real, with galaxies inside it. And as space-time expands, the galaxies, or superclusters of galaxies, are carried along by this expansion.
After Hubble's discovery of the expansion, everyone set out to, including Einstein, to rework general relativity to be able to account for this cosmic problem.
The expansion of the universe takes place primarily in the huge spaces between clusters of galaxies, so small objects like galaxies or the Earth do not expand. It is the mutual gravitational attraction between objects in the solar system and in galaxies or star clusters which prevent them from participating in the general expansion of the universe. We also have the phenomenon of cosmic microwave background radiation. This is low-intensity radio noise, with a 3 degrees Kelvin black body temperature, almost uniform in intensity in all directions. The CMBR is a huge cosmological mystery.
We have evidence of the expanding universe and the CMBR. However, parts of the Big Bang Theory are unable to resolve certain conflicts. The prime example is eternal inflation, which is in conflict with the Hubble constant that describes the expansion rate of the universe. Einstein's space-time equations don't work with eternal inflation. A mathematical way around eternal inflation would be a cyclic universe, one that expands and then contracts repeatedly. But then the physics problem of entropy pops up, which is a measure of disorder and chaos in systems. With a cyclic universe, entropy and disorder would increase so much that nothing in the universe would be able to form. No stars, galaxies, or planets. If eternal inflation and the cyclic universe are discarded, we would then have to accept the fact that the universe had a beginning. Most astrophysicists have trouble with that. Nova and I both have grave epistemological concerns on the notion of eternal inflation, as did Einstein, since he modified his own equations to counteract just this problem as discussed earlier in the module.
At present, we know of 4 fundamental forces operating in nature under normal condition. They are the gravitational force, electromagnetic force, strong nuclear force, and weak nuclear force.
These 4 forces govern all interactions within the universe. Again, beyond the scope of our course, but I'm just pointing them out.
Here are some more facts about the 4 fundamental forces.
So the electromagnetic force holds the electrons and atoms together. The nuclear forces work only inside the nucleus, and We know that there's an even more fundamental particle than protons and neutrons called the quarks.
We know actual distances in space. No matter how you slice it, it is 25 trillion miles to our nearest star neighbor. We know the actual chemical composition of the stars and bodies in space because of our ability to analyze light to determine chemical structure. We know that as soon as we jump off the planet, there is no left, right, up, down, north, or south. We know that there is a speed limit on how fast an object can move through the universe. It is 186,000 miles per second, as shown to us by Einstein in his first paper on relativity in 1905. We also know that our star and its planets is just one of over 600 billion stars like it that make up our own Milky Way galaxy. In the larger space of the universe, there are millions upon millions of galaxies. Please make note that void spaces are generally bigger than galaxies. One fundamental fact limits our view of the universe. Light from objects farther away than a certain distance, defined by the travel time of light in the lifetime of the universe, has not yet reached us. We also know that the universe has no middle, top, bottom, edge, or any other such property. We are space and time travelers that voyage through the cosmos on a little rock in space. This little rock is spinning on its axis at 1100 miles per hour, while we, the Earth, move at 66,000 miles per hour to complete our yearly orbit. We are captured by the gravitational pull of a G2V class star. Around this G2V class thermonuclear bomb that we call a star, our rock orbits every 365 days to return to the same position it was relative to the star the year before. And we call that a year of time. And of course, stuck with our sun on its 225 million year orbit around the Milky Way galaxy, we are moving with the speed of the sun at 600,000 miles per hour, and the whole local supercluster is moving at 1.5 million miles per hour towards the great attractor beyond. So where are we? All we can say is that we are somewhere in the expanding universe, but not in any special part of it.
We have no idea where we are. It's space. It's gigantic.
Astrobiology connects the cosmos and the origins of life. Biological life as we know it, plants and animals, are carbon-based life forms. It is the only thing we can identify as life, alive or living. Many forms of carbon exist, such as diamonds and graphite, but they are not alive. Since carbon-based life is the only form of life we can identify, we are limited in our search because we have no idea what a non-carbon-based life form would appear like. How would we know?
This is why we search for water in the solar system and beyond, because we know carbon-based life forms use water.
So at the base level, in our search for extraterrestrial life, we are guided by three basic items. Search for carbon compounds, liquid water, and the chemicals called amino acids, the building blocks of DNA proteins of living things. The existence of life depends on chemical, physical properties of matter. We know life can exist in liquid water. We know for liquid water to exist on a space object, it must be a certain distance away from a star to be liquid. Therefore, we search for regions called habitability zones.
Planets too close to stars, like Mercury, have no liquid water. Planets like Pluto, too far away, are frozen. So we look for the Goldilocks habitability zones.
Searches for advanced civilizations try to detect the radio signals. This is the Search for Extraterrestrial Intelligence SETI project. I have a question for you. If a civilization doesn't send out radio signals, does that mean that intelligent life does not exist elsewhere in the universe? Humans have been sending out radio wave signals into space for just over a little more than a century.
So please understand what that means. At the speed of radiation, 186,000 miles a second, we've only been able to send out radio waves for a century. That's only 100 light-year distance. We know all of the stars within 100 light years of Earth, and none of them have bodies on them. The Milky Way is 100,000 light years across. So a signal that has reached 100 light years from Earth is not much.
Finally, the Drake equation asks the question, how many civilizations are likely to exist in the Milky Way? The short answer is a lot. In conclusion, astrobiology and planetary geology are the new frontiers of space. I hope you enjoyed the course and have gained an added interest in our universe. Thank you.
Professor Quasar thanks you very much. So in this module we looked at the Big Bang Theory, which is just a theory, the people who study the origins of the universe, the concept of the expanding universe and the steady state theory, the four fundamental forces in the universe, and the Drake equation, which allows us to calculate how many civilizations may exist.